We'll go to the next presentation, which brings us back to this side of the Atlantic Ocean. As a matter of fact, to Philadelphia, where not too long ago DFI had its Super Pile event. And Martin McDermott from Keller will talk a little bit about the Riverwalk there project, and apparently they delivered a knockout punch. Martin, floor is yours.
Thank you, Gerald. Yes, I just wanted to say thanks for the opportunity with DFI and its money. It's a great venue there we can share. This project, the Riverwalk project, was really collaboration with an owner who was motivated, their geotechnical engineer and design team who was open to listen and options to add value, and then the team with that was John McElroy with Langen, who was representing the owner, and then Jeff Goodwin, who was our geotechnical and structural engineering consultant to bring a value-added approach to this project. Next slide, please. Just wanted to share a little piece of history. This is Valley Forge in 1777, 78, that winter. And my father was an artist, born and raised in Philadelphia, and a great historian. But as they were losing the Revolutionary War badly, he wrote, "Naked and starving as they are, we cannot enough admire the incomparable patience and fidelity of the soldiery." And that's really the spirit of who we are, and I think our industry, you know, that we need to continue to persevere and push on. Next slide, please. This is a little bird's eye video that's going to come onto your screen. You're looking south down into Philadelphia. Couple of iconic structures there. City Hall, 1901, when that was completed, was the tallest building in the world at 548 feet. And the Ben Franklin Bridge, when that was completed in 1928, was the longest suspension bridge in the world. So next slide, please. This is your basic site plan. There's the site on the east bank of the Schuylkill River, and the shot shows you to the left, the photograph. You can see the drill rig sitting on this open lot. It's a prime piece of property that they were looking to develop this property along the Schuylkill River with the active railroads along the west and south boundaries. Next slide. Just a project overview. To the left or the west, you can see Schuylkill Yards, 30th Street Station. Project is just prime location. There's a lot of gentrification. A lot of people are moving back into the city, and so that's why this particular site was so desirable. Next slide. Just historic Newton Coal Yard from 1929. It was an industrial site. You can see the cobblestone streets. That's how Philadelphia is pretty much known for them. Next slide. You can see here we are looking north, the active rail that was present along the site. On the Schuylkill River, you can see a sheet pile wall, an old steam crane, steam hammer installing that sheet pile wall over there. Next slide. And just here's the entrance to the old yard in 1955, where they sold sand, cement, coal, and etc. So you can see the rail yard leading into the yard itself. Next slide. And here's a view looking west. This is from the historic Pennsylvania Railroad Bridge, and that is the 30th Street Station in Philadelphia. So the main northeast corridor for Amtrak Railroad. Next, please. Here I'm going to hand it off to my colleague, John McElroy, who is the lead geotechnical engineer for Langen for the owner on this project. Take it away, John.
Thank you, Martin, and good morning, all. So what we're seeing here is the the owner's concept of what they wanted to build. You can see 30th Street Station, as Martin said, and the Amtrak and SEPTA Regional Rail Viaduct that comes across the river and by the site and right next to JFK Boulevard. What the owner had thought to do is to build a podium level section across the full footprint with two towers. One tower being about 26 stories high and the other one 32. The first one being built on the shorter one and on the right, and the taller one on the left. And actually, you can kind of see, ghosted in there is a potential third tower that's may come in the future. Next slide. Here is Tower 2 under construction with Tower 1 in the background. This is taken probably 2 months ago, so we're probably up to the top of the core there now. Next slide. A little bit of regional geology. The key point is that where the site lies, and in this yellow zone, which you can see identify here as Trenton gravel, but underneath that Trenton gravel, you'll see this orange striped mass that's slightly to the northwest. It goes underneath that material, and that's the material that we had to really deal with here. It is a mica schist. It's an old, very old formation, Cambrian Ordovician of age, 500 million years in the making. It has, and if we go next slide, undergone quite a bit of deformation and metamorphism. Actually, 5 episodes of deformation and 2 stages of metamorphism really makes this material very complex. It's mainly a schist, both a quartz and feldspar schist along with a peltic schist. So it's challenging, as we'll see. It does have a saprolite layer above it, very weathered and soil-like, weathered zone, and it can be very deeply weathered at times, which we'll see as we go through the presentation. Next slide, please. Right. So here is a cross section running east to west up Market Street, which is one of the center main street in Philadelphia. Just giving you an idea of where our site is, which is to the left would be the Schuylkill River. Actually, to the right is the Delaware River, New Jersey on the other side. But you can see in the site location, we're at a high point of where our rock is, which is good. But we do have saprolite we have to deal with, and we do have the overburden materials of that Trenton gravel, the other material which kind of pinches out before we get to the site. Next slide, please. So here's an idea. This is this previous slide, and this slide's taken from a nice reference by Gwynn and Ferguson in '91, looking at where does rock begin in Philadelphia, is the name of it, and it's kind of a very telling reference. You can see in that document, they kind of look at trying to break down the material in a saprolite, which is again just a soil-like material, 0 RQD, little limited recovery, and then weathered rock, partly weathered rock, and sound schist. And we'll kind of use those reference or these categories as we talk later. But it's really key. Below, materials are not so rigorously defined in most boring logs and many site investigations. Top of saprolite is defined as auger refusal, and top of rock just by trichome bit refusal. Next slide. So we went about for the owner to develop a field investigation program and foundation recommendations. We went through a couple stages of field investigation, as you can see here, the black one being our initial study with soil borings and some probes. And then once, based on the, that preliminary study, went back and did some additional borings to better define the rock for, the developing concept, and especially to check into some areas that were suspect, problems that we had needed to refine our understanding of the bedrock. And we'll see that in the next couple slides. Next slide, please. So here is a summary of, side by side of all of the borings taken here. I'm not going to delve into this much, but I wanted to indicate the gray is our bedrock, right? The green is the saprolite above it. What's really, telling here is that the light gray is kind of that, mostly weathered rock. The light gray is the weathered rock, and then the dark gray is more sound intact rock. Well, you can see there's no real transition one to the other. It bops all over the place, and you have some darker gray underneath, above some lighter gray, and especially you can see some areas where we have some lighter gray to really deep depths, as seen in the middle of these this figure, and we'll see it again on the next figure. Next slide, please. So here's a couple cross sections. Our key concern was right around this LBS3 kind of intersection of cross section A and cross section B, where we did encounter very weathered rock to depth. And if we go to the next slide, we'll see how that plays out in a cross section. Right, so here we're seeing, our overburden materials, a lot of fill on the top, as is, typical along the Philadelphia waterways and waterfronts. The sandy silt, the decomposed rock, but then you can see we dipped down very deep, right, 80 feet plus before we hit some competent rock. But we're going through a lot of weathered materials, but we'll see later on that these, the RQDs and recoveries are very poor. Next slide, please. This is a little blow up of that area. We did actually, 4 additional borings in and around that area. And we're seeing, a whole variety of recoveries and RQDs, some as low as, 0 to 20% RQD in this area. Next slide, please. Maybe one reason we're seeing that is there's an old map of Philadelphia looking at some of the hills in the area, as by John Hill. But the key, the blue is our site, but you can see also this maps some of the old waterways as well. And you can see right down the middle of that blue rectangle, their site is, you have a waterway coming through. And a lot of this, the schist is very degradable with exposure, with water, and that could be the result of, or a reason why we have that deeper zone of weathered material there. Next slide, please. So here's an indicator of some of the borings, especially in that zone where we're looking at rock right on site with similar recoveries and RQDs that have drastically different rock strengths too. The green indicates 174 recovery RQD and a unconfined compressive strength of 770 psi, whereas a similar rock in yellow, 100/68, only has 650 psi, and we see that type of variation. And Martin will explain or show you a little bit more in when he picks up after me. Next slide, please. So what we did was, give the weather material for caissons. We recommended caisson foundations here. And we do it. Philly does a lot of caisson foundations over the years. And for the weathered rock, we gave a 45 KSF bearing, end bearing, and a 5 KSF side friction. Whereas for the intact rock, we bumped that up to 100 KSF or 10. But remember, to get in that one area, to get down to the intact rock, we had to go through 60 feet, 50 feet of some of the more weathered material. Next slide, please. So what we decided to do is, indicate to the owner that it's really prudent to go out and do some full-scale load testing on test caissons to really look at the actual end bearing and side friction values using, bi-directional load testing, Osterberg test cells. That way we could both look at the rock, shallow rock, the weathered materials, and we could look at the deeper rock and decide, what those values are and what would be prudent design values to use. And this is as Martin said, very cooperative owner, and was willing to do this, and got Keller on board to implement a load test program that Martin and Jeff will discuss next. Next slide, please. Oh, here's Martin.
Okay, thanks, John. So real quick, this is the boring location plan. It shows you the top of rock elevations, and generally, you can go as deep as 55 feet and as shallow as 20. And next slide. And just we'll focus in on this LB1, the differentially weathered rock mass, and what this means. So if you look at the first core recovery at 31 feet, you had 100% recovery, 100% RQD. That's hard rock. We're the contractors. We got to drill this rock out. Then you get the weaker zones, so the next two runs were poor rock quality, then another hard layer, and then a weaker layer, hard. So the risk for the contractors, how much of this rock are we going to have to drill to get to the 100 KSF material? Well, the answer, would be, wow, that's a lot. So the object was, let's try to maximize the end bearing on this rock and reduce the risk of and size of these shafts. Next slide. Here's some more pictures of the core and the core recoveries. You can see in that LB3, gee whiz, you had to go down like 60, 70 feet before you're going to get to the rock. So that adds time and money and risk to the job. Next slide. So what we did we did a series of air tracks across the site, targeted the most high capacity shafts. Basically, they were as low as under 1,000 kips to up to 6,500 kips. So we targeted the high capacity shafts, used the air tracks to just get qualify where the top of the rock was and estimate where we would hit this more competent rock. Next slide. And the base design for our foundation, the strategy that Jeff Goodwin, who's going to jump on here, will talk a little bit more about it. But basically, at that 6,500 kip, we would be drilling 8-foot diameter shafts in over 10-foot length rock sockets, maybe up to 18-foot rock socket lengths, to using the more mainstream values of the shaft. So Jeff, I'm just going to turn it over to you.
All right. All right, thanks, Martin. Hey, as Martin said, when we looked at what the basis of the original design was, we wanted to go in and really try to tailor the enhancements to design based on our knowledge of the geology, but also looking at what Keller was bringing to the table. And so how we situated the redesign was looking at what kind of tooling and what kind of drill rigs were going to be used for the construction of the shafts. We were looking at using 1 meter and 1.5 meter casing with the bower rigs. And so we looked how we could reduce the shaft diameters, reduce the shaft lengths, and then also try to minimize the extension into the upper rock stratums. And so we came up with our load test program looking at some of the worst case locations. And those you can see from the previous slides where we had either extensive weathered rock or layered good rock, weathered rock, good rock, weathered rock. So what we came up with were using two bi-directional load tests. The first shaft was going to use a two-stage test where when we did our first stage, we were only going to place concrete in the lower portion of the shaft so that we could try to test and reach ultimate capacity in the side shear in the rock socket. And then after we achieved that, place concrete in the rest of the shaft so that we would have additional reaction to try to take end bearing as high as possible. The second load test then would be really our more high capacity end bearing test or punch out test as it's called, where we were testing a smaller diameter at the base of the shaft so that we could impart as high of unit loads as possible. The last portion that we wanted to really test with the load test program is, test the drilling methods, test the toolings that we were having, and also calibrate inspection because as we've said that this was a collaboration, but it wasn't just limited to our three parties. Whereas Langen was the original geotechnical engineer, and we were the geotechnical engineer for the redesign for Keller, there was also third-party inspection on the site. And so we wanted to make sure that the inspection during the production shafts knew what we were looking for when we did the shaft construction. Next. All right, so we picked in these locations for the two shafts, one where we had shallow good rock, and then in that area that John had alluded to where we had some of the deepest rock that was encountered. We wanted to test these so we could see what some of the worst case scenarios would be on the site so that we could minimize risk during construction across the site. Next. Our first test shaft where we had two-stage testing, you can see we placed concrete in the bottom 8 feet of the shaft, which was in competent rock. And we were going to run our first stage of load testing to try to maximize the unit loads and side shear. Next. From this, in the load test, you can see we applied a maximum load of a little over 1,600 kips, and upward we only had about 1/4 inch of movement in side shear, so we never actually even reached ultimate side shear capacity. And downward we were about 1/10 of an inch. So again, we didn't, fully maximize the loads that we could work with on the project. Next slide. When we added concrete, we added additional reaction forces. So here we are able to test up to over 2,000 kips, and you can see we were able to start approaching where ultimate capacity would be when we would expect it around 1/4 inch or so of upward movement. Here we got to about just under 2/10 of an inch of upward side shear. But you can see that even with all the additional reaction, we had really negligible additional downward end bearing load movement. Next. The second load test shaft where we had the decomposed rock and competent rock, here we went with a punch out test so that we could really put high unit loads in end bearing. So here you can see we have the The shaft set, we had about 30 feet of concrete placed in rock sockets in both decomposed rock and the better quality rock. We used the strain gauges so that we could, impart our unit side shear loads within the different sockets. Next. Here's a good example. This is one of the core sections that we brought out of the shaft, where we had poor rock above it, and then we got a nice solid chunk of the Wissahickon schist come out, and then we had poor rock below it, and we had this layering effect within the shafts. And so one of our goals of testing would be, well, what happens if we have a good layer of rock, and then we find out that we have an inferior layer of decomposed rock below that. So that's why we picked some of these drilled shaft locations for the testing, so that we could find out what happens in that case, and would it affect the overall capacity of these shafts. Next. Here you can see the results of this second shaft were really pretty substantial. We applied almost 5,000 kips to the shaft. Upward, we were reaching ultimate capacity. We were at almost a ½ inch of movement, upward side shear. And then downward, we had about 0.16 inches of deflection. So really successful load test from that standpoint, because we were trying to maximize unit loads from this whole test program, and we really felt that we were able to achieve this. Next. Okay, so when we look at what we actually found, the test shaft 1, which was near LBS 1, end bearing, we applied 870 KSF with under 1/10 of an inch deflection for end bearing, which was significantly higher than anyone had ever anticipated in the Wissahickon schist. The side shear for the schist was 25 to 28 KSF with about 1/8 of an inch of deflection. And this was pretty close to what has been determined previously there in Philadelphia. At test shaft 2, we found that we had almost 1,000 KSF end bearing load imparted, and with only 0.16 inches of deflection. So really, loads were very, very high for end bearing, and that's what would give us a lot of opportunity to look at cost savings, but also keeping a level of conservatism. Side shear in the rock, we had from 16 to 42 KSF in the different zones of weathered rock and more competent rock, with almost a ½ inch deflection. So next slide. So when we look at what we had and then what we found, as Martin had said originally, based on the original design, we were going to have shaft diameters typically 5 to 8 foot diameter and sockets up to 20 foot. What we looked at then was, as a result of this testing and trying to meet all the goals of testing, we were able to enhance this overall design. We settled on a rock side shear capacity of 16 KSF, and that was really based on what overall factors we had and what we needed to apply. End bearing, we had 240 KSF, but we were able to reduce these overall shaft diameters to fit the equipment that Keller was bringing to the site with the 1 meter and 1.5 meter casing. We also had an overall reduction in the shaft lengths, so that we had maximum went from 20 feet sockets at 8 foot diameter to 10 foot socket at 5 foot diameter. And really what we found that the controls on these socket lengths were the uplift, required uplift capacity, and also the required lateral loads for these shafts. As a result, we also went through a redesign of the steel reinforcement, and we calibrated the the overall engineering inspection to the site, so they knew what to expect. The drilling team on the site knew what to expect, and everyone knew how to answer questions as they arose. And so it gave us a real good opportunity to assess the equipment, make minor tweaks prior to going into construction. And I think one of this last bullet is really what allowed us to really move full speed ahead, in that we had a series of more lightly loaded shafts. And the day after we performed the load test, we released all those shafts for construction. This bought us, several weeks of time where we could analyze some more complicated loading conditions with high shear, with high moments, and it gave us time so that while they were in production, there were no delays to the site based on the redesign. They just moved full speed ahead, and by the time they were finishing these lower loaded shafts, we had the final design in the more complicated cases completed. Next, or I guess I'm turning it back over to you, Martin.
Yeah.
We'll
I know we got
go through the construction.
Because thanks, Jeff. So just real quick, here's the rig coming in, doing the layout. Next slide, please. And so this was our target. We had the segmental casing, cardonic link, and the casing driver system using 1 meter and 16 50 millimeter segmental casing. Next slide. There's advancing the segmental casing down with the rock auger. And basically this would, once you penetrate it, the decomposed rock and into the top of the bedrock in one continuous advance of the casing, the shaft was stable, you controlled the groundwater, reduced the softening, and it was really ideal. Instead of 5 diameters and different pipes, etc., we had two setups. Next slide. This is just a picture of the 1 meter casing driver, the auger clamp, and then the 1650 millimeter casing and auger clamp. Obstructions, that was we removed the obstructions. That's always risk and dollar amount. We did that ahead of time. We had the owner understood that, which was great. So that moved things along. Next, please. And then just the drill setup with the rebar cage, with the T-heads for uplift, and then we're able to pour in the dry by free falling the concrete. That was a big plus. Next, please. And we had some challenges with low overhead issue, railroad, active freight line. We had to bring in a low overhead rig and permanent casing in some cases, but actually, as a result of a lot of the savings, it wasn't a big impact to the owner on the budget on the job. Next, please. And just in summary, so it was 207 shaft locations from 3 to 8 foot diameter, was over 10,500 lineal feet. Average depth was 55 foot, and it was 8,900 cubic yards of concrete. When we did the VE, we didn't know how deep we were going to have to go. So we basically kept that 55 foot, just 3 and 5 foot diameter. So you can see a 7,200 cubic yard net was the projected. Then when we did the testing, we said, gee whiz, we can probably get this down to about 30 foot length. And that equated to 6,300 foot of drill foot length and 4,100 cubic yards. And then at the end of the project, as built condition, we averaged 32 foot shaft length, about 7,000 lineal foot of drill length, and just close to 4,500 cubic yards. So just in the end result, just that volume of concrete, we put, almost half, we reduced the concrete quantity by half that we're installing into the ground. So just from a sustainability standpoint, that was pretty special and obvious time, cost, execution savings on the job. So sorry we ran over there.
No problems. Thank you very much for a very interesting presentation, Martin, John, and Jeff. The last slide said it all. Not only, and that was only the direct savings in the concrete cost that you showed. We have quite a bit more in a shorter amount of time that you're on site and all that good stuff, which increase the savings even more so.